This section 4.2 is on graphs of exponential functions. The first section, we will see some properties of basic exponential graphs. There are two different shapes, and we'll do a couple problems with them, varying a couple things so you can see what shapes to look out for, what kind of things are important. And then the second section is determining the equation of an exponential graph. If you're given an exponential graph, one thing is to realize it has that shape, and then the next part is, okay, I need to figure out the equation. How am I going to do that? All right, but the first thing we'll talk about are the properties and the picture of exponential graphs. And what we're going to do is we start with the very basic, quote unquote, basic exponential graphs, which is y equals b to the x. So that's when a equals 1 and k equals 0. I'll remind you, our generic is y equals a times b to the x plus k. Our generic exponential function, our graph, we are dealing with a equals 1 and b equals 0, or k equals 0, sorry. Now, one thing I'll remind you as well, b had a couple rules. We had to have b positive, and b could not equal 1. And that separation, so b between 0 and 1 and b greater than 1, gives us two different pictures for exponential graphs. I'm going to sketch them in a little bit. You'll notice the important thing of how I'm going to graph these. I'm going to point out the important things. It doesn't have to be super precise. I mean, really, I'm not even going to be able to tell you what b is, just that it's going to look like this. Right, so the one on the left, I will do b between 0 and 1. And the one on the right will be when b is bigger than 1. All right, now one of the most important properties of exponential graphs is they have what we actually learned a little bit about it last chapter, something called a horizontal asymptote. But you can't figure it out the same way that we did with a rational function. When it comes to exponential graphs, specifically the exponential graph y equals b to the x, they have horizontal asymptote of y equals 0. They both have the same 1, and that's why I'm pointing it out first and putting it on both pictures. Of y equals 0. It doesn't really look like a y. Oops. Let me redo that. Y equals 0. All right, another thing, if you plug in 0 for x, just to see the y-intercept, for each one, y equals b to the 0, which is 1. That's just to give us the starting point of how we're going to graph this. When the graphs change a little bit, a changes the y-intercept, k changes the y-intercept. You don't necessarily use that so much, but I'm just going to plot the y-intercept for each one of these as well. They are both the same, which is at 1. Let me actually fill in x and y axis to avoid any possible confusion. All right, now what's going to happen, this is where the main difference of these graphs come in. When b is between 0 and 1, it is a decreasing graph. And an exponential graph looks like this. It sort of looks like a downward slope, but it's for the decreasing one, it slows down slower and slower. And one thing I want to remind you that we talked about last chapter with horizontal asymptotes and asymptotes in general is as we go towards an asymptote, it doesn't touch. Right, so this, as we go towards infinity, remember that right in behavior as x goes to infinity, as we go to the right, the y value is gonna go towards 0 but stay above the x-axis, right? Because it's not going to touch the asymptote. It gets very close to it, it never touches it. Now, like I had, I'll write in here one way to characterize the difference that we're going to see. When b is between 0 and 1 is decreasing. Sort of the way my brain likes to think about it is decreasing is always, and increasing are always measured from left to right, the way we read. So decreasing, it's decreasing because it's going down as we move to the right. But what happens with all exponential functions is you have this horizontal asymptote, and it sort of looks like the graph bends away from the asymptote. It's kind of like bending away from it. If we went farther and farther left, you'd see it get steeper and steeper. And we'll graph an example. You'll be able to see it almost looks vertical. It gets so steep. Now the main difference between the b between 0 and 1 and b greater than 1 is when b is greater than 1, it's increasing. It has the same shape. It pretty much looks like the same graph flipped over the y-axis. I kind of made this one a little steeper over here than it was over here, but that's okay. But the same idea. This time as we go to the left, it's going to still stay above the x-axis, but it gets very close. But the way to characterize this one, as I just said, when b is bigger than 1, it's increasing. Well, it's always helpful, once again, with exponential functions to think about them bending away from it. And sometimes you can think about the shape as being part of a roller coaster. Think about if you're on a roller coaster, this one's going down. You're not going to go down forever because eventually you'd hit the ground. So that's to slowly level off. If you go up a roller coaster, most of them don't just level off, go flat. They bend up until you start getting close to the top. So that's one way to think about it, I suppose. There are a couple other properties that are important. I have all the other properties listed down here. The domain of exponential functions is -infinity to infinity. That means you can plug in any number and get out a real number. I mean, no dividing by 0, nothing like that. The range is 0 to infinity, and we don't include 0. Right, the reason this is the way it is the range is the y values. The lowest it goes, it gets really, really close to the horizontal asymptote, but stays above. And so that's when we use the parentheses. Is when we're really close to a number, but not quite touching it. The thing I have right here bolded because it's very important is the horizontal asymptote of y equals 0. And the other thing I pointed out, if b is positive or bigger than 1, it's increasing. If b is between 0 and 1, it's decreasing. But these are the standard graphs. These are y equals b to the x. If we change a, if we make a negative, which we'll see, it'll flip over the x-axis. If we change k, and it's positive, it'll move it up because adding numbers move our graphs up, subtracting numbers move our graphs down. In general, what you'll find, and I like to just mention this here, is that in general, the horizontal asymptote is y equals k. All right, this one is not coincidental that k was 0 and the horizontal asymptote was 0. If k is 2, that means we are going to add 2. We're going to move the graph up 2. The horizontal asymptote will go up 2. Right, but I would definitely write these down, make these pictures. This is really the background of this. Right, but like I said, what I want to do now before we go to the problems is just graph one of these. You can see how it works. I'll graph one of each. For the one between 0 and 1, I'll just do 1/2, and for the one bigger than 1, I'll do 2. That's pretty typical examples. So we got y equals 1/2 raised to the x. I won't do them both on the same graph. And hit zoom 6. All right, so that was between 0 and 1. That was our decreasing one. And you'll see it looks pretty much this shape. As we go to the right, it's going to get close to 0. Even though it looks kind of weird, it's not going to actually hit the x-axis. If remember what we did with the table before, if we type in like a really big number, it will pretty much look like 0 in our calculator because the decimal points. And it falls off so fast. But at 100, it's something like 8 times e to negative 31 power, meaning there are 30 zeros in front of that 8. It's a very small number, close to 0. One thing I also like to look at when we talk about these exponential functions is what the base means a little bit. So when the base is smaller than 1, the reason it's decreasing is to go from 1 to the next, it's like multiplying by 1/2. You don't need to remember all this, but I just like to explain what's going on. So if we figure out what we get when we plug in 0, we get 1. If we go to the next whole number 1, it should be 1/2 of that, which it is. If we go to the next number 2, it should be 1/2 of 0.5, which is 0.25. And the next number 3, half of 0.25 is 0.125, and so on. So if we keep taking half of this number, eventually it gets really close to 0. Now I'll graph 1 bigger than 1. Like I said, I'll graph y equals 2 to the x. We can just see that. It's going to look exactly like the one I graphed, the general shape. It's increasing. As we go to the left, if I type in a big negative number, it's basically going to be 0. If I do negative 100, right, we get that same number from before. It's pretty much 0. An 8 with 30 zeros in front of it. And the base being 2 means if I type in numbers one after the other, it's going to double every time. When we plug in 0, we get 1. When we plug in the next whole number 1, we get double that, 2. When we plug in 2, we double that with 4. When we plug in 3, we double the previous one to get 8. That's just a nice way to think about exponential functions. I will reiterate, you are not required to memorize that stuff, but it's a good way to think about it. All right, so what we got in the first little section is a couple matching problems. You can do these in your calculator, and I'm not opposed to that. However, I just want to talk about the different shapes that you get if you change some stuff in the equation. Okay. So the directions for the first one here, it says match the following graphs with the corresponding formulas. You have 4 here. On the homework, there will be like little answer boxes, and you would select this one's A, this one's B, this one's C, this one's D, whichever one you get. So we want to match with one over here. And what I like to do, what I think is a little bit easier, is to look at a graph that would have been one of our normal ones. So if you look at the top left here, this is the same shape as our y equals b to the x with b bigger than 1. Right? It follows the same shape. It's above the x-axis. It's increasing and it's bending away from our exponential graph like that. So this is like y equals b to the x, and b is bigger than 1. Now if you look at the choices here, there's only one of those. B and C have B between 0 and 1, so it's not going to be either one of those. And D has a negative sign in front of it. Because it has a negative sign in front of it, this flips over the x-axis. Right, that's what negative signs do in front of equations. That means the only possible choice is A. It's the only one that works. Now, if you look at the one right below it, it's also above the x-axis. It looks like one of our normal ones. You notice the other two are not above. And it is the decreasing. It's above, but as we move to the right, it's going down. And let me use a different color here. So this one down here, the bottom left, this looks like one of our normal ones, y equals b to the x, and b is between 0 and 1. And the only other normal one is c. Right, so if our graph looks like it's above the horizontal asymptote, you won't have a negative sign. And that's just kind of nice to know. Now the other two come from flipping these graphs. So you just, if you want to do this by hand, you just ask yourself, okay, I'll pick the top right one to do next. Which one is this flipped? Is it when we flip the -1/4 or we flip the 4 to the x? Well, if we kind of think about unflipping this over the x-axis, it would look like this somewhat. So imagine if we unflipped it. If we took it back above the x-axis, it would look like this, and it's decreasing, which means the base is less than 1. So it has to be that one. Choice B, -1/4 to the x power. It can be a little confusing if you don't think about it this way, because it is an increasing graph itself. But the fact that it came from a normal flipped or normally unflipped decreasing graph is why it's this one. And you can also graph in your calculator to check. Now by process of elimination, that tells you what the last one is. The last one is got to be the -4 to the x. But you can see why that makes sense. If we unflip this one, it is our increasing graph. And our increasing graph has a base bigger than 1. I do encourage you, when you do this, to actually try to do it by hand and think about it. You have unlimited attempts on the homework. It's a good way to remind yourself of some graph transformations as well. All right, so the next one is really going to be about how the different base changes. So if the base is bigger than 1, we know it's increasing. If it's smaller than 1, it's decreasing. But how do we know how much it's increasing or decreasing by? So I'm going to go ahead and write in a comment here on the side how you would think about this, because if you try to graph all these on your calculator at once to compare them, you might get the stuff way too close together and you might not be able to tell the difference. All right, so b is bigger than 1 is increasing. All right, that's in general. But the bigger it is, the more it increases. Meaning a base of 3 is going to increase more than base of 2. And I'll show you with an example on the calculator. But the bigger it is, the more it is increasing. So y equals 2 to the x will be steeper than y equals 1 to the x. I guess that's a good way to kind of write it too. It's more increasing or steeper. Now when b is between 0 and 1, the graph is decreasing. We know that. And this one's kind of backwards. The more it is decreasing, I guess it's not really backwards, but you kind of think about it differently. But we can't go negative. Well, we think about being farther away from 1, we want to be closer to 0. The closer it is to 0, the more it is decreasing. Another way to think about it is that it is more steep in a decreasing way. So I'll go through this problem specifically. I just want to talk about why this is and show you in the calculator, because these numbers, if you do graph them, they are all pretty close together. It might not be that easy to talk about the difference. Right, but I'm going to compare the two, like I mentioned, 2 to the x and 3 to the x. The 2 to the x is going to be in blue, 3 to the x is going to be in red. And you'll see that the red is in fact more steep. Now what we talked about before, what the base means, this actually makes more sense. So if we go to the table and look at the numbers I had plugged in before, you get 1 when you plug in 0 for each. But for y equals 2 to the x, it's going to double. Y equals 3 to the x, it's going to triple every time. So if the numbers go up a lot faster, it is way more steep. The same idea goes when the base is between 0 and 1. If we're doing half for y equals 1/2 to the x, that's going to decrease slower than y equals 1/3 to the x, because if we multiply something by 1/3, it's smaller than multiplying by 1/2. Okay. All right, but to get back to this question specifically, what I want to just kind of point out here, each one of these will go with one of them. You'll notice that the first and third one, the base is bigger than 1, so it's going to be increasing, each of these. And the bigger of the two is a steeper increase. So 1.4 is much bigger than 1.19, it's steeper. All right, so now what you do is you look at the two increasing graphs. One is in red, one is in blue. Blue is definitely more steep. Okay, so blue is the more steep increasing graph, which means it goes to that one. And red is increasing, but it's less steep. It's gonna go to the other one. Right, the other two choices have a base of 0.9 and 0.71. They're both between 0 and 1. Those are both decreasing. And the one that's further away from 1, or the one that's closer to 0, is the steeper one. 0.71 is further away from 1 or closer to 0 than 0.9. So this one is the steeper one. It's steeper and decreasing. So if you look at the two choices here, the black line labeled as K and the green line labeled as G are the two decreasing one, and the green one is definitely more steep. If you think about trying to walk along these paths, it's going to be a lot easier to walk on something like K than G. G's pretty steep. You might just lose your footing and fall down. Okay, so the steeper graph, G, green, goes with the bottom one. And then the less steep one, the black one labeled as K, goes with the other. Right, but that's a very useful thing about exponential functions, especially when we do some things with applications. Knowing that the base, the actual number of the base matters, is a good thing to know. Okay, but one of the main things, pretty much the main type of problem of this section, is to be able to determine the equation of an exponential graph. If you're looking at all this right now, it's honestly more wordy than it ends up being. But the important thing when you have a graph, I'll scroll back up. When you have a graph and you want to figure out the exponential equation, you have to do things in the correct order. You really won't be able to do them in any order you want, just because you'll just go around in circles. Right? But the idea here, I'm going to underline this one even though it's highlighted. This is our equation of an exponential graph. I'll remind you of that, and I'm going to go ahead and write it down. You will not be told this, just as a reminder, on a test or anything. You do need to know the equation. But what is of extreme importance is that the first thing you must figure out is k. If you don't figure out k first, you are not going to figure out a and b, and that's just the way it's going to be. K has so much influence over what you might think of a and b as that you'll actually have a lot of trouble figuring out a and b. So we must figure out k first. I'm going to do this first problem like one step at a time. So we're going to go ahead and do k first. And I want to remind you, k is the horizontal asymptote number. So if we look at this first one, the horizontal asymptote, you can see that it kind of flattens out over here going to the left. And that's at y equals 0. Since you can only see so much of the graph and you can't, zoom out or anything, it's got to go towards the number it really looks like it is. But since the horizontal asymptote looks like it's y equals 0, our k value actually is 0. And what you want to do, like I have up here in the directions, is plug that in and use it. Right. Once you know what k is, plug it in to our formula here. F of x equals a times b to the x. Now normally I wouldn't write plus 0, but to emphasize what we're doing, we're plugging in k equals 0. And now I'm going to just not write that 0 in. F of x equals a times b to the x. Right. The second thing you want to do is look at the y-intercept. The y-intercept is like when we plug in x equals 0, that will let us solve for a. Right, so the next thing we want to plug in is the y-intercept. Our y-intercept here is x equals 0 and y equals -2. So let's go ahead and plug it in. Just remember those questions from the beginning of last section. We'll plug it in. And we get -2 equals a times b to the 0. B to the 0 is 1. Because anything to the 0 is 1. So we are left with -2 equals a. Now this is purely only the case that a is the y-intercept because k is 0. We'll see in the next example that doesn't need to be what happens. If k is not 0, a will not be the y-intercept. Right, but just like after we figured out k, now once you figure out a, take the equation and plug it in. You already know what k is and you plug that in, so don't worry about that anymore. We want to plug in our a now, and that is -2. And a can be negative all at once. It's just b cannot be negative. Right, the third and final step is to figure out b. And to figure out b, what you need to do is you need to find any other point on the graph where you can actually see the x and y value. Which for us, we have one at 1,6. Right, one thing you don't want to do not plug in a number that's close to the horizontal asymptote because it never actually touches the horizontal asymptote. You cannot plug in -4, 0, for example. It's not touching. So we do not want to plug in near the horizontal asymptote. Right, you just do not want to do that. But we will plug in our other point. We have x equals 1 and y equals 6. On all these graphs, you'll be able to see at least one other point besides the y-intercept. Now we'll plug in that. We got 6 equals -2 times b to the 1 power. B to the 1 power is just b, so that's great. 6 equals -2 times b. And then we solve for b, divide by -2 on each side, and we get b is... Oh, you know what? I definitely need to plug in y equals -6 because b is not supposed to be negative. My apologies, this should be -6. That point is definitely -6 for y. That's negative. -6 over -2 is +3 for b. And now that we've got b, we will finally have our answer. You plug it in. And we get f of x equals -2 times 3 to the x. Just like we talked about in last section, you cannot combine these. -2 is to the first power, 3 is to the x power. This is it. Right, but I got one more here like this with k not 0, so you can see that a is not going to just be the y-intercept. Right, but I'll just go through the order. I'm going to start by writing down the equation again. F of x equals a times b to the x plus k. And we are supposed to figure out k first. K is the number where the horizontal asymptote is. You can see it's leveling off at -3 to the left here. So the horizontal asymptote is y equals 3. What that's telling us is k equals 3. And we'll plug that in just like last time. You don't want to disregard it. You plug it in. F of x equals a times b to the x plus 3. Right. Next, we use the y-intercept to figure out a. We plug in x equals 0 and y equals -2. And we plug it into the equation we plugged in for k. Remember, that's the order. We got -2 equals a times b to the 0 plus 3. Right, now go ahead, b to the 0 is just 1. Now, of course, I guess it's getting too late in the day. I keep missing negative signs, and some of you watching this probably realize this. K is -3 because we're at y equals -3. So let me go ahead and fix that in the formula. K is -3. We have a to the a times b to the x minus 3. Right, now I'm where I need to be. B to the 0 equals 1. We got -2 equals a times 1 is a minus 3. And then we add 3 to each side. And we get a equals 1. Right. But you can see here, the y-intercept's not at -1. A is not matching that. Right, I'm going to go ahead and plug that in like last time. F of x equals a, which is now 1, times b to the x power minus 3. If you're like me, you don't actually want to write the 1 down. You don't have to, because multiplying by 1 it does nothing. We got f of x equals b to the x minus 3. And finally, the last part is to figure out b by plugging in another number. I will say this one's pretty steep, but when you work the problems out on your own, it's not as blurry. This one passes through the point 1, 2. I know the way we're looking at it on the screen, it almost looks like it could be through 1, 3, but when you work on the homework, it's not blurry like this. It's more clear. So we plug in our other point, x equals 1 and y equals 2, and we'll get our b. We got 2 equals b to the 1 minus 3. Add 3 to each side because b to the 1 is just b. And we have b equals 5. All right, and then we'll finish up by plugging that in, and we will have our final answer. F of x equals 5 to the x minus 3. Right, one thing you can definitely do, which I'll do with this last one, is graph it so you can see that it matches and the horizontal asymptote's doing what we thought it would. So f of x equals 5 to the x minus 3. I'm going to hit zoom 6 to put us in our standard window. It doesn't draw in the horizontal asymptote for us, but we can see -3. It's getting pretty close to that. If you plug in some really negative numbers for the table, -100, we can see the y value is pretty much -3. I will remind you it's not actually -3. It's just there's not enough decimal point. There's so many zeros at the decimal point. The calculator doesn't see anything but zeros. And then the 2 points our graph passed through that we use, the y-intercept was -2, and also passed through the point 1, 2. If we plug in 0, we get our y-intercept of -2, and if we plugged in 1, we get our y value of 2. So everything matches, and we're good to go. Once again, I'll go back to the graph to finish up. You can see it has that same shape. And that is really what we need from exponential functions, understanding what the shape of them are, how the base affects it, and if you are given a graph, which is one of the 2 main ways you might actually use this, graphing them, how do you figure out the equation?